So notice in big bold letters, I tell you, include all numeric values in every calculation, right? Answers that just show up are bad. So in terms of the data, you're going to record the angle. Either you use your app or I got an app on my phone. We need the angle. We'll see where that plays out later on. Then you're going to need your total time. In terms of data, this is all you need. You need to record where it starts, where it stops, and the total amount of time. And again, make sure your times are close together. So from that, then you're going to start to do these calculations, okay? We're going to look at this in two distinct halves. What's happening up the inclined plane, what's happening going down the inclined plane. So you're going to go from positive velocity to zero, zero back to a negative velocity. Then you have a whole bunch of questions to answer. Be specific when you answer these questions. Just don't say, oh, yes or no, okay? When I tell you to explain, I mean explain. So you're going to have two graphs, okay? You're going to have a position time graph that's going to look like this. You're going to have a velocity time graph that looks like this, okay? When you get done, that's a very crude version of it, but that's basically what it's going to look like. So when you answer 5 and 6 on the bottom of page 1, okay, I've given you the formula for acceleration, so you can use that formula. You can look at this in terms of sign. You can look at this in terms of, hey, is it speeding up or slowing down? There's a whole bunch of different ways you can answer 5 and 6. I don't care. Just make sure that you explain that thought process. Now, when you get over here to questions 15 through 19, this is where you're going to do the calculations for initial velocity and acceleration. Listen to me and view this from my perspective. I'm going to have two different sets of groups. I don't have an answer key. I can't look at your velocity and go, oh, it should have been 1.1, they got 1.4, oh, they did it wrong. I don't have an answer key. I have an idea of what your velocity should be. If you get something like 200 meters per second, something's gone a little bit wrong. It's about 2/3 the speed of sound. Cool, probably not. Also, this is not like a stunt show. I don't want you to like put your ramps in opposite direction and try and jump one ramp to the other.
What?
Okay? Bad things will happen, that's why.
No.
Okay. Now, so the only thing I can grade on 15 through 19 is your process. Okay? That's the only thing that I can grade. I can only grade your process. Now, when you get to question number 21, and I've given you this formula, and later on you'll see where it comes from once we get into forces. But the theoretical acceleration is going to be negative 9.8 meters per second squared times the sine of the angle. This is where you're going to use the angle of this. Okay? It's typically around 2 to 3 degrees. Negative 9.8 times the sine of the angle. Make sure you are not in radian mode, or you're going to get an answer that makes no sense whatsoever. Make sure that you're in degree mode. Now, when you get to question number 22, you're going to calculate experimental error. So let me explain how I want experimental error done. So experimental error, and we're going to do this a lot, is the absolute value between your theoretical value and your experimental value divided by your theoretical value times 100. So your theoretical value is going to be what you get from question number 21, okay? Based upon this angle and a frictionless surface, this is what you should get for your acceleration. So that's basically going to be your answer to number 21. Okay, so your answer to number 21 is your theoretical value. Your answer to number 17 is your experimental value. So that's going to be number 17. This is an absolute value. That way we don't have to worry about negatives. And then you're going to multiply by 100. This is certainly different for everybody. Again, I emphasize this. Show your work. Pay attention, word of caution, pay attention to the negative signs. Okay? So you're going to have a negative theoretical value minus another negative experimental value divided by that theoretical. I'm just telling you, watch how you handle the signs mathematically. Then you multiply by 100 to get it as a percentage. When you get to question number 23, this is where you're going to draw this particle diagram with the vectors again. So on number 23, here's what I've given you. Here's the box, there's the card. Okay? So on the space below, I tell you, draw velocity and acceleration vectors on the way up, 3 velocity vectors and 3 accelerations, and then you're going to do the same thing on the coming back down. So you're going to come in here on the way up and you're going to say, oh, here's V1. Okay? Just draw an arrow, V1. Now, when you draw V2, one of two things is going to happen to V2. Either V2 is going to get bigger or V2 is going to get smaller. That's it. That's it. So if you think it's slowing down on the way up, draw smaller velocity vectors. If you think it's speeding up on the way up, there's some other issues, but then you can draw them bigger. Okay? So, then you want to draw acceleration vectors. Which direction are the acceleration vectors going to point? They're either going to point down or they're going to point up. They're either going to point in the same direction or the opposite direction. Now, here's the story. The whole point of this lab is to force you to look at acceleration. So when you look at acceleration, your acceleration vectors are either going to be changing or they're going to be the exact same. If you want me to think those acceleration vectors are getting bigger or smaller, you clearly draw them where they're getting bigger or smaller. If you think they're the exact same length, you draw them the exact same length. I am not going to guess. It's like, oh, I don't know, Matt, did you want them to get smaller? Did you want, oh, I don't know. I'll spend an hour measuring and trying to figure that. No, okay? Either the acceleration vectors are the same length or they're getting bigger or smaller. That's what you have to decide. Now, when you get to number 25, you're going to take a ball and you're going to throw it up in the air. And it's going to go up to a maximum height of 5 meters. 5 meters is about twice the height of this ceiling. Okay? So you're going to throw it, start a stopwatch, boom. When it lands, the entire trip took exactly 2 seconds. So you're here, throw it, time it, 2 seconds later, it lands, it went up to a height of 5 meters. So you're going to do the exact same thing here. You're going to draw a position time graph, you're going to draw a velocity time graph, you're going to calculate velocity on the way up, velocity on the way down. Okay, I'm done. You're on your own. Due on Monday. Got any questions? Ask as we go. All right, Cohen.